All right, folks, now we can get started. We're at our second session of short talks. These will be 10-minute talks. I'll give the speaker a warning at 8 minutes, and then an alarm will go off, and I will drag them off stage. So we'll have 2 more minutes of questions, and during which time the other speaker will come up. Okay, our first speaker, J.B. Ruhl. Thank you.
Thank you. First, before I talk about sort of the segue from the lunch panel to my presentation, I want to welcome you to the law school. I'm a lawyer, and we have a growing interest in this space. We have a program here called the Program on Law and Innovation, and one of our primary focal points is the use of technology, including AI, in law, and then the impacts of AI on society and how law must respond. So we call it AI for Law and Law for AI. So the posters outside illustrate the wonderful good that can come from using data science and AI, machine learning, natural language processing, et cetera, to learn more about solutions to environmental, economic, and social problems. So there's much good to come of this, but I am a lawyer, which means I am hardwired to think about what can go wrong and how we deal with it. And I think the lunch panel illustrated that in the space of criminal justice and privacy, there is much potential for things to go wrong, and how do we deal with that? As my interest in AI and law grew, I looked around for sort of a repository of writing by legal scholars on the subject. And the Social Science Research Network, SSRN, of course, has a series of e-journals that collect papers, and they have a legal journal series. And so I looked for the legal journal on AI and law, and there wasn't one that I could find, at least. I called SSRN and said, where is the Artificial Intelligence in Law e-journal? I can't find it. We don't have one, they said. And I said, well, I'd be happy to start one. And they said, are you sure there's going to be anything, written about it? I said, I'll tell you what. You have, back archives. I'm going to give you some keywords, and you go search your archives with those keywords and tell me if you think this is a viable journal. They called the next day and said, we're in. We now have 750 papers authored by legal scholars, oftentimes in collaboration with other disciplines, addressing a wide variety of issues that I'll get into. This goes beyond, certainly beyond criminal justice and privacy. Some of the dominant topics, having now edited the journal for a year and a half, and just today at lunch, worked through 3 issues of the journal for 1 week, 15 different articles. Just show you the pace, right? So weapons, automated intelligent weapons, privacy, employment decisions, treatment of labor, social benefits, autonomous cars, of course, evidentiary issues, we touched on that at the panel, due process, how do we administer AI in legal settings, and of course a lot of writing about the ethics. So the topics at today's panel were both on point but not at all exhaustive. And so as I began to edit this journal and think about, how do I make sense of all this, I developed this matrix as a way of just thinking about what's this article about. And across the top of the matrix is sort of the ideal way we might think about how law is developed and assessed, right? So we have to start out with some kind of a theory about what it is we care about, concepts, frameworks, right? And as we develop that theory, then we can start to ask important ethical questions about our moral duties, the ethics of AI. And then we can develop policies, right? Policies that are answers. How do we want to manage that theory and ethics in a way that then we can make those decisions actionable? And law then is needed to implement policy. You have to get it on the ground through law. And of course we can say, well, we've got the law, but what's the actual practice? Are people following the law? Are the legal administrators following the law? And then we can after time, take a retrospective look at the experience, and that ought to then loop back into our understanding of theory, policy, ethics, et cetera. On the side, then I have the four big kind of categories that seem to help classify what questions are being asked in the law and AI interface. The top one is not one I'll spend much time on today. It's about the use of AI in actual legal practice. It's already widely used in discovery, in contract due diligence, transactional due diligence. It's starting to get traction in legal search, just in other words, what cases are on point on this. And all I'll say is that many lawyers are petrified that AI is going to replace them, and they're probably partially correct that AI can take over a lot of functions that lawyers accomplished that was kind of routinizable or commodifiable. But on the flip side is AI may really make lawyers even better at what they do. I think our today's symposium and certainly lunch panel is more interested in the second, third, and fourth rows, right? So the second is the use of AI in legal administration itself, judging and administering the law, right? And so turning over bail decisions to machine learning, for example, versus human judge. The big debate is, you know, which is less discriminatory? Or in what ways is one discriminatory that the other isn't, and which do we care more about or less about? Law for AI. How do we wrestle this thing in a way that we're comfortable that we've got legal restrictions or legal facilitations of the use of AI? And then, ironically, it may be that the only way to really kind of make AI obey the law is with more AI, right? So machine learning to monitor machine learning. And that kind of gets a little bit problematic, right? But how can humans monitor machine learning if we don't know how to interrogate the black box, so to speak? So we can, you know, take any one of these and walk across, right? Can AI actually judge? Is AI judging? What is going on when machine learning is being used to set bail or probation or other tasks that judges are asked to do, but they're relying heavily on this, you know, machine learning program, and they say, okay, whatever. Is that judging? Is the judge really performing the judge's duties? Is the AI performing the judge's duties? Does machine learning discriminate, right? In the law, we have intentional discrimination, and then we have a concept called differential impact, right? And so in some cases, in order to establish a claim, you must show intentional discrimination. In some cases, you don't, but it's not clear that either of those concepts really matches up well with what might happen when machine learning sort of embeds differences and turns out to differentiate between populations or groups in ways that we find in the law, you know, illegal or offensive, but is it really the same thing as discrimination? It's kind of something we have to think about before we can then develop an ethics and a policy response. And then, right, what are the ethics of turning over decisions about legal administration to machines and then asking machines to then monitor the machines? So I use this matrix as a way of thinking about what it is exactly that is sort of on the minds of legal scholars who are anticipating the ethical decisions we have to make, the policy decisions we have to make, and then ultimately, how do we craft law? And that's the hard part. We can come up with ethical conclusions and policy conclusions. And in my law school classes, then I'll say, okay, great first-year property students, now write a law that implements that. How do you actually do that, right? How are we actually going to craft legal text to activate our decisions about the ethical policy and legal objectives of regulating AI or using AI? And lastly, I'll say, how is this different? I mean, law is always constantly taking on new technologies, new social issues. How is this different? What is it about it that makes it something that is more of a puzzle for the legal mind than other past technological challenges? And I think the lunch panel kind of addressed it in a way I think it can be expressed concisely. It's very difficult, right, to understand, interrogate, and explain what's going on. How do you, this is the Darbert question, how do you put the machine learning on the stand and say, how is it exactly you arrived at that decision? Right? We can do that to a human expert. We can even do that to a really super stats up human expert, run us through your linear regression. But if there's no kind of record of how the machine learning program actually arrived at decisions, very hard to square that with our current conception of due process, of evidence, of how we conduct trials, and how we use expertise in science in the courtroom, in administrative agencies, and other legal institutions. So I think it is qualitatively quite different than the past challenges technology has thrown at us. Thank you. I guess I have a minute for questions, right? Great, so you've all figured out the legal solution, so write it down. What's the law of AI? And when you have your answer, please hand it in. I'll grade it. Thanks.
We do have a question.
Oh, there is a question, sorry.
So those lawyers are concerned that they might be replaced. Are they concerned in terms of researching prior case law and sort of finding similar cases? Is that how they're concerned about being replaced, or is it in what way?
Well, it's twofold. One is that AI has the potential to make the practice of law far more efficient. So if it takes less time to find the right case, that's fewer billable hours for lawyers. That's one, right? But the other is truly that there are, so for example, e-discovery has seriously just simply eliminated many legal jobs, so to speak, because it does what the lawyer used to do, sifting through documents and matching relevant documents, matching up the documents with issues, et cetera, that, AI does it. You don't need a human to do it. You simply don't. It's not a matter of just being more efficient. It's actually better, faster. Whether it's cheaper or not is debatable. But that really is a replacing versus sort of making more efficient versus then I think there's a lot of opportunity for AI to enhance the delivery of legal services, even at very high sophisticated levels.
And I was going to, if I can ask one follow-up question, how do you think it can best augment lawyers in the practice of law? What's the biggest?
So I think that stepping back and thinking, what is an expert lawyer, a bespoke lawyer, really offering a client, say, judgment about the likelihood of us winning this case, okay? So, and I was one, right? I consider myself kind of an expert. When I was asked that question, what were the data points I had in order to make that judgment? I might know the judge. I might have handled 2 cases in front of that judge. I might have friends who know more, et cetera. So maybe I have some data points, both experiential and actual sort of objective observation. What AI can allow you to do, I think, is draw on vast numbers of data points, right? That then either sort of reinforce your bespoke judgment, or if those data points result in sort of like, hey, that's not the way I see it, maybe I ought to go and reassess my judgment, or maybe there's something wrong with the data point. But that's really what's starting to happen in legal practice, is you're seeing AI used, particularly in predictive analytics, to increase kind of what the bespoke lawyer has at his or her disposal upon which to make judgments and provide advice. So I think that's really going to facilitate at the higher end legal practice. Yeah.
There was one more question.
Okay.
Short question and short answer.
Okay.
Yeah. So one topic I didn't hear you address, and it may have been embedded in your matrix, and I just didn't see it. But one of the problems that we are now becoming aware of in terms of artificial intelligence, particularly in things like sentencing, is that artificial intelligence tends to exacerbate historical trends, not change the trends. And so to the extent that we have a bias in our sentencing, because our judges are as biased as the rest of us, that the use of artificial intelligence will drive those biases in a negative way rather than help correct for them.
Yeah, and the questions in each of those boxes were just examples of what hundreds of questions that could be asked. But I would put that in kind of the AI for legal administration, and then at the far right, I had practice and experience. So I think we really have to monitor what comes out of the use of AI and ask, wait a minute, how did that produce a result that is, in some way, shape, or form suggests that something's gone wrong? So we have to really monitor.
And what I'm saying is that I think we all recognize now that there is a bias in our sentencing. Why are, African Americans so dramatically overrepresented in our jails? And we all the evidence of stop and frisk and the likelihood that if you're black male, you are going to be stopped by the police regardless of your background, track record, what you were doing, etc. So AI may exacerbate that because that's what our history is.
Well, that would go into the policy box then. That would be, in other words, before we decide, we have to decide what is our policy. Is that risk great enough that we would conclude let's not go that route? That's a policy question.
This is an interesting conversation. We should continue over the break. Thank you very much.
Thank you.
Let's have another.
Oh, thank you.
All right, next up is statistical thinking for data science with Chris Fonnesbeck.
Thanks very much. I'm going to talk about some much easier problems, just ones that you need to be aware of. So I'm going to talk about some issues that are statistical in nature that are, I think, important to data science, but data science by its very nature is interdisciplinary, and so not everybody comes from a statistics background. I don't even really, and I'm in the biostatistics department. So it's important to be aware of these, and I've only got time to do one or two of these in 10 minutes. So let's start with cats. I'm going to motivate this first one with cats. Cat data. So way back in 1989, in the New York Times, I remember this article from when I was an undergraduate. There's an article that appeared called On Landing Like a Cat. It's a fact. And I'll just read, for those of you who can't read it from all the way back there, just the first few sentences here. It says, every year scores of cats fall from open windows in New York City. From June 4th through November 4th, 1984, for instance, 132 such victims were admitted to the Animal Medical Center on 62nd Street in Manhattan. Most of the cats landed on concrete. Most survived. And the article, which you can still find online, it goes on to actually give you a lot of the data. So 21 of 22 fell 7+ stories, survived. 2 of them fell together, okay. 40% fell at nighttime, and the range of heights of the buildings ranged from 2 to 32 stories. The cat that fell 32 stories was named Sabrina, suffered a mild lung puncture and a chipped tooth, and she was released after 48 hours. Just for context, the AT&T building downtown is 33 stories. And of course, there was this surprising positive correlation between the longer you fell and the higher probability you had of surviving. So, what was going on here? And so the rest of the article is, subject matter experts hypothesizing why this might be the case. And some say, well, it had time to turn in midair, or it had time to relax, maybe even like little flying squirrel flaps of skin under their arms. What was going on here? Anybody want to guess? Oh yeah, I can ask you guys. You guys all, so half of the audience, are aware of these issues that I'm going to raise today. But it actually, the hint was in the line that I read you. It said 132 such victims were admitted to the Animal Medical Center. So you don't typically bring the dead cats to the medical center, right? So we're only looking at the data. We're only looking at, if not the survivors, the ones that had a reasonable chance of surviving to begin with. And so this is kind of a silly, funny issue, but it ran in the New York Times, and I see it raised on like Hacker News from time to time. Somebody will bring this article up. How did this happen? This happens when you have issues like this with found data, right? And this is very common in data science. You find a data set, and you try to figure out what to do with it. And so what these represent are, convenience samples. These are expedient data, usually a lot more. The ones that are bigger are more interesting to us. They're not collected by any sort of sampling scheme usually, and they're being used to answer questions that were never intended by the collectors of the data. And the important thing with this data set, of course, is that there was a bunch of missing data, right? The ones that were missing were correlated with the outcome, which is really, really bad. And missing data can arise in all sorts of settings: experimental settings, observational studies, epidemiological studies, and of course, found data like this. And the important thing with this particular type of missingness is that it results in a non-representative sample. It's not related to the underlying population of interest, i.e. all falling cats in this case. So, these are statistical issues. And often, in the age of data science where I think, as Eugene pointed out, you can just learn Python and get scikit-learn, or even worse, you can get TensorFlow and run a gigantic deep neural network on something. Some of these issues are forgotten. And one of the big misconceptions is, in the notion of that the big data will solve a lot of these problems. So, do these problems go away with larger data sets? There was only 132 cats. So what if we had 132,000 falling cats? Would that have solved, the issue? And in the case of big data, you got search results, Twitter feeds, Facebook data, and so on. And some people believe that the problems do kind of go away. So way back in 2008, there was an article that appeared in Wired by Chris Anderson called "The End of Theory" that essentially postulated that correlation's good enough and you don't need models anymore. So with enough data, the numbers kind of speak for themselves. And you can go back further in history, 1930s, ALFRED LANDON, for the Americans in the audience, he was a presidential candidate, a Republican presidential candidate that ran against FDR just after the New Deal was introduced, so there was some general unhappiness. And even back then, they tried to predict the outcomes of elections. The nice thing about these sorts of data science problems, if you want to call them that, is you always get feedback as to how well your predictions did. And in this case, the Literary Digest, which was a respected magazine at the time, they shouldered the responsibility of trying to forecast the result, and it tried to do this huge public opinion poll, postal public opinion poll. So they mailed out, tried to reach 10 million people in the electorate. They got 2.4 million returns, which in 1936 is big data indeed. After tabulating those 2.4 million returns, they announced the conclusion that Landon would win by convincing 55 to 41%. And of course, since we've never had a President Landon, you know the outcome. Roosevelt crushed Landon. I'm just going to leave this up here for a little while, a sea of blue. And to make things worse, for the Literary Digest, there's a guy by the name of George GALLUP, who was a son of an Iowa dairy farmer, who decided to do some random sampling. So he created a much smaller survey, a mere 50,000 sampled, but importantly done by a random sampling scheme. Today's polls are much, much smaller, more than an order of magnitude smaller than this. And he at least got the direction of the question right. So he overpredicted for FDR, but he got the right answer. And so the difference here, of course, election data is not found data, but similar problems creep in. A representative sample can only be assured by random sampling, and so a small random sample beats a large non-random sample pretty much every time. A couple years after that misprediction, the American Institute of Public Opinion went in and did a sample survey, a random sample survey to determine the cause of the poor result. And of course, those that did not receive a ballot were heavily biased towards, you can see here, FDR supporters. And then on top of that, those that returned their ballot were heavily biased in that direction as well. So by 1938, that magazine had actually ceased production. That essentially killed that magazine. So the issue I'm raising here is bias. So here I'm not talking about bias in the sense of connoting judgment on something, but just there being a systematically different estimate from the true population parameter. Sort of formally, mathematically, that's what it looks like. The bias of some estimator is just the expected value of that estimator compared to its true underlying value. And so we can actually go in and use simulation, like Lena suggested earlier on. What if we can use some simulation to see what happens to bias as our data gets larger? And of course, to answer these questions, that's where you have to learn Python. You go and learn Python. And just a few lines here. So this is just a simple loop that goes in for a range of sample sizes, generates 1,000 samples, and when the sample is negative, there's a 50% chance that one's going to drop out. And when you do that, you can see that, so there's 10 through 10,000, it has really no effect. In fact, it makes things worse, right? It makes things, it makes you more confident in your wrong answer, essentially. So why do we collect a lot of data? Well, any kind of nice estimator of accuracy like mean squared error, it's a combination of variance and bias. And the variance goes away as n gets large, but the bias doesn't. I'll just finish off with, kind of a newer example having to do with a public health tool generated by the charitable arm of Google, google.org. This was the Google flu trends example. And it tried to find correlations between 50 million search terms and basically 1,152 data points, which are CDC measurements of flu, incidence of flu. And it was touted as a very big victory for big data. It did very, very well in the early years. But in 2009, it drastically underestimated things. And then the peak of the 2013 flu season, it overestimated by 140%. This was, now if you visit it, that also is gone. And the problem with this, and the problem with all of these examples that I've been using, is that there was no data generating model underneath here. That's what you always have to consider in these cases. That's really the only way to get around the bias. The Google flu trends model was very simple. It predicted this week's, used last week's CDC reports to, tried to predict this week's CDC reports from last week's search terms. And the data generating process underneath was changing. The algorithm, the search algorithm keeps changing over time. And so it was using a phenomenological model rather than a mechanistic model. Of course, you'll see articles like this now that tries to use perhaps better data to try to predict things from, say, Twitter, which at least has open data. And I tried to kind of end on a sort of a good note, is that a newer study has come out using Twitter information to try to predict flu outcomes. But what it does is it pairs this biased information with a mechanistic model and some understanding about how flu is actually working. And it purports to give slightly better results. This is actually pretty brand new work. So quite apart from the notion that data can speak to it for itself, it really can't. We can't live without the models. So, I'll just end with this picture. This is a colleague of mine. You might have seen this before. This is the data science Venn diagram. And so data scientists can be described as sort of the intersection of three domains. There's we call it hacking skills, computer science, statistics, and whatever domain that you're applying your data science to. Data science is in the middle, and if you ignore the statistics, you're in the danger zone. So I'll end there.
All right, we have a few minutes for some
Questions?
Nick.
We were talking about the 50,000 data points, and you said that it should be randomly selected. Sorry. Concerning the 50,000 data points, and you mentioned that it needs to be a random selection. How important is that it's truly a random selection, and how important is it that the model you're trying to predict, so like likely voters, for example?
It's preferable if your data is random. If it's not, you have to know about it and do something about it. So as long as you know what the bias is, that's why I'm stressing this data generating model. If you know how that bias manifests itself and you can model it, that's fine. Not everything can be randomized. It's often not ethical to randomize. Where you can, it makes your life a lot easier.
Time for one more question, if there is one. All right, well, let's thank the speaker. All right, folks, up next is Nancy Cox, and we're going to do some phenome phishing for genetic discovery.
This is a really fun thing to be doing today. And boy, am I glad I'm not a lawyer. That's hard. Going phishing is easy by comparison. So there was a paper just published in Science. Lisa Bastrash was the lead author. And it had come up with a really fun and interesting new tool that actually scores the phenome, we call it. So this is the phenotypes that you can look at in electronic health records. And the idea that she had was to create scores phenome scores for Mendelian disease genes by taking the descriptions, the phenotypic descriptions of what characteristics people with these Mendelian diseases have, basically creating a score to be able to characterize that phenome from electronic health records. So it's just basically a tally of the phenome you expect for any given Mendelian disease, weighted by the log inverse of the frequency of that particular phenotype in electronic health records, so that the rarer, more canonical phenotypes would get heavier weights, okay? And so that could be applied in the context of the large electronic health records at Vanderbilt, and with that could show that people diagnosed with any of these Mendelian diseases do indeed have higher phenome risk scores for the Mendelian disease than people without the Mendelian diseases. And there was basically, very little overlap between those with and without the Mendelian disease in these phenome risk scores. With the exception of the disease here, phenylketonuria, and the reason there's no difference there is that phenylketonuria is screened at birth, and we identify all children at risk for phenylketonuria and change their diets. So they don't actually have any phenotypic manifestations of their disease as long as they follow the prescribed diet. And in fact, children having been diagnosed at birth with phenylketonuria don't have any difference in their phenomes from people who are healthy, which is a very good thing, a victory, as it were, of genetics. But among the other interesting features of applying these phenome risk scores across the entire medical record was to discover that for some recessive Mendelian diseases where we expect to see 2 different mutations in people who have disease, there are some people having fairly high phenome risk scores who are merely heterozygotes. So the homozygotes are indicated here, but there are people who are carriers of just one mutant allele who have fairly strong symptoms for the disease. And in fact, we have learned in other ways that for many Mendelian diseases that we think of as autosomal recessive, requiring 2 different mutant alleles at the same gene to actually lead to disease. But in fact, when you can look across tens of thousands of individuals, heterozygotes may often be heterozygotes, people with just one copy of a mutant allele, can be at statistically significantly increased risk of each of the phenotypes that make up that Mendelian disease. They don't have all of them. They don't have all of them from birth, the way people with 2 mutant alleles would have. But they are at risk, at increased risk for many of those features. And so this allows us a concrete way of quantifying that risk for the Mendelian disease genes, where these phenome risk scores could be built from pre-existing information. So the existing knowledge about what medical diseases people with these Mendelian disease mutations get over their lifetimes. So we're now going to go fishing with that same sort of idea in the biobank at Vanderbilt. So BioVU is the name of the biobank. There's more than 250,000 samples now in BioVU, linked to a really high quality electronic health record going back more than 20 years in some individuals, but 10 to 15 years. We have genome interrogation on about half of those samples by the end of this year. And we're using that genetic data to essentially impute the transcript levels for each gene, so measurement of the gene expression, and potentially also metabolomes. So this is a variety of additional omics that are possible because of the high heritability of those traits to impute using the genome variation. So the idea there is that we use a reference panel like GTEx, where we've measured transcriptomes and have genome variation. We build predictive models, and we can show that we have high quality out-of-sample prediction performance for about 18,000 genes and long non-coding RNAs. And so then those predictive models can be applied to subjects where we just have the genome data and essentially impute the transcript levels, and allows us to create a gene by medical phenome catalog where we can basically look up the relationship between genes and the medical phenome. So the idea here is that people have probably talked about phenome-wide association studies. So this is a gene-based phenome-wide association study. So instead of asking, as we have for decades in genetics, what genes, what genetic risk factors are associated with asthma or diabetes or any given phenotype, we're basically asking, what does this gene do? And more precisely, what is the natural variation in the expression of this gene associate with across the entire medical phenome? So that's what we have in this catalog where we're going to go fishing. And we are really going to go fishing because colleagues came to us after some zebrafish experiments where they had, after an ENU mutagenesis experiment, identified some mutant zebrafish, so that the zebrafish are shorter, they have craniofacial malformations, so their heads are smaller on average than the wild type animals. The fish are actually shorter also than the wild type animals. And that's because they traced the mutation to a particular gene that forms an important machine that moves the big fibrillar collagens out of cells. And because the collagen can't be moved from the cells where it's made out into the bones, skin, extracellular matrix where it does its job, it accumulates inside the cells. So in the wild type animals, you don't see much collagen still inside the cells, but in several different kinds of cells, you can see that the mutant animals really accumulate collagen in the cells. It just doesn't get out. It turns out that this gene that was discovered this way is one of two that must create this protein machine that moves the collagens out. So the second gene in the pair is RGP1, and they knocked that out in the zebrafish just to see how similar the phenotypes were. Phenotypes are very similar, both at the sort of gross phenotypic level. They have the skeletal abnormalities with the short, kind of kinky tails and small heads. But they also are very, very similar at the cellular level. So that by comparison with the wild type animals, there's huge accumulations of collagen in chondrocytes and neurocoats. So we looked at, so then it turned out there were patients just reported at that time with mutations in that RIC1 gene that was the first discovery. They have exactly the same sort of phenotype with an accumulation of collagen in the cells. They came to us to see what phenome in BioVU was associated with the reduced expression of these genes. And it turns out that in BioVU, we see all of the phenotypes that are seen in patients with the mutations, and that includes bone, fracture, connective tissue disorders, tooth development, tooth eruption difficulties, valve disorders, skin disorders, esophageal, gut, and digestive disorders, disorders of the extracellular matrix, and neurological and psychiatric disorders. So the kids are short, they have abnormal tooth development and eruption, they have they have gut and digestive disorders, other disorders of the extracellular matrix, they all have developmental delay and very severe ADHD, and a couple of the kids have autism as well. We see additional neuropsychiatric disorders. So the idea was to go fishing for that phenome, literally fishing, using a phenome risk score for the phenome that we see for RIC1 and RGP1 associated with the reduced genetically determined expression of these genes, to find other genes affecting human disease through this same mechanism, and indeed found fibrillar collagens that have these associations, and several other genes, some of which, so one of which is an enzyme that provides the energy for that RIC1 RGP1 machine that moves the fibrillar collagens out. Another one is a protein that stabilizes, strengthens the extracellular matrix, which is where what most fibrillar collagens do. Another is associated, does ER-associated degradation of misfolded proteins, which is what happens to these fibrillar collagens if they don't get out. So they're misfolded in the ER. So a lot of, and then these others, we don't know what they do, but we can try to knock them out in zebrafish and discover that. But it's a fantastic opportunity to really expand discoveries by using the phenome, which turns out to be much more powerful than anything else at extending the discoveries. So with that, I'll close and happy to take questions.
All right, we have time for one or two quick questions.
You guys can come fishing anytime, though. Come on. Thanks.
All right, let's have another round of applause for our speaker. Next up is William Doyle, who'll be using spatial analysis to understand access to higher education.
I should do that. Hi, everybody. Have I got the mic on? Yep. My name is Will Doyle. I'm a faculty member over at Peabody. And I want to talk about a series of studies that we've done to document and then understand the importance of kind of how many colleges are close to how many people. So in thinking about like why higher education might be important, I don't think I have to do a ton of justification to an audience of faculty members and students. But really quickly, to put a scale on this is data from the National Longitudinal Survey of Youth, looking at people by 2010 who are between 27 and 31 years old. The people with a bachelor's degree were making about $15,000 a year more than the people with just a high school diploma. So there's been no decline in the economic value of higher education. Higher education is closely aligned with various civic outcomes, including voting. In the 2008 election, voting among bachelor's degree recipients was about 75%, compared with 50% of people with just a high school diploma. So it matters. Whether you go to college really does matter. And my work is around the policies that can increase access to higher education. There's kind of two things that I generally want to establish. What are the policies that can help us get more people into higher education? And what does higher education do in a causal sense? Does it actually impact these various outcomes that I've put up here? Or is it just kind of an association? And one of the key aspects that seems really important is what are the differences based on where people live? Now, higher education, we don't tend to think of higher education as being highly localized in the way we think of as K-12 education. Vanderbilt students come from all over the world to attend here. But most people go to college really close to home. 50% of students go to college within 20 miles of where they were living previously. 80% of college students go to college within 50 miles of where they're living. So it's much more local than I think is generally appreciated. And so it becomes important to measure that level of geographic information. And the set of data sources that we use to do that, and by we I mean myself and Ben Skinner, who's a former doctoral student here and is now at the University of Virginia. We use data from the Census Bureau to look at geographic information, the American Community Survey. We brought in data from the National Center for Education Statistics on every single college and university in the United States. And then longitudinal data, tracking students over time from a couple of different surveys, the National Longitudinal Survey of Youth and the Education Longitudinal Survey, which is exactly what it sounds like. And the tools, just really quickly to give you a sense of the tools that we're using to do this, are in our studio is the basic setup. So what we wanted to do with all of this was document geographic opportunity. Now, the typical way this is done, and it had been done before we really got into this, was just looking at whether or not you had a college or university in a given geographic area. Do you have a college or university in your county was by far the most common measure. And so this is what, if we look, this is Williamson County in Tennessee. Does Williamson County have a public two-year college? Well, no. But this shows all the public two-year colleges that are kind of around Williamson County in Tennessee. And if we would visualize that more broadly for the United States, this shows for the entire US, for every single county, does that county have any college at all? And we can break that down in a variety of different ways. Does the county have a public 4-year? Does it have a public 2-year? And so on. But it's obviously really limited to look at things this way because it's not just like, do you have a college in your county? You might live like right next to a college, but it's one county over or something like that. It's really, how close do you live to how many colleges? And then what type? Are they public 4-year or 2-year? Are they expensive or inexpensive? That's what seems to really matter in terms of thinking about geographic opportunity. So to figure this out, we started by measuring the distance from every single county centroid to every single college in the United States. So for the 3,000 counties, we just measured up all the distances from there to all the different colleges. We did the same thing with census tracts. So for the 73,000 or so census tracts, how far are the population centers of all those census tracts to all the different colleges? So then we put all that together. We used a summative measure of how far are you away from how many colleges? It's a well-known technique that we learned about using inverse distance weighting. So if you visualize it that way, it looks like this. So this is the Move to Ohio map, right? So this is just how close these counties are to how many different colleges across the United States. Now this is just mechanical in some sense because most of the colleges in the United States were founded over here, and there's just a ton more colleges in Pennsylvania, Ohio, the New England states, and so on. So yeah, they're like a lot closer to a lot more colleges. What we really think matters in terms of college opportunity is particularly the in-states and the publics. In-state public institutions are where most people go, about 80% of college students. It's much less expensive to go in-state. It's much less expensive to go to a community college. And it's generally easier to get in. So if you look at it that way, there we go. We'll start with the in-state public 2 years. So this shows for every county in the United States how close the people in that county are to how many colleges. And so you can see the real differences in geographic opportunity, many of which are directly tied to state policy. So in North Carolina, California, and particularly the eastern parts of Texas, people live close to a lot of community colleges. In other states, they live quite far. They don't have any community colleges nearby. So you can see the real differences, for example, between Illinois and Indiana and the level of college opportunity available for the people in those states. Okay, so we use this in two different ways. The first way, so this just shows the same thing with these restrictions. The first way was kind of the splashy kind of public version of this. We went ahead and for policymakers and kind of the general public, we ranked every state, particularly with respect to their college affordability. How expensive is it to go to those nearby colleges? And how does that compare with the income that people make in those states? So for Tennessee, for example, attending a public 2-year, which is where 28% of people go, requires about 17% of family income overall. And if you break that down a little bit further, if you're talking about people who make between $0 and $30,000, it's actually more like 37% of their income, and obviously less as you go up the income scale. And we provided both a map of the US, which shows for all the different states, here's the percent of income required to attend. And we also broke this down by every census tract in every state. So if you zoom in on Nashville here, in areas south of Nashville, the net price of the nearby colleges is about $8,500. That compares with an income in that census tract of about $92,000. Head north, an average income of $11,000, so a very similar price, but that requires a substantial amount of family income, imposing amount of family income to be able to attend. So these differences across states really mask differences within states. And just in case anybody wanted to know, we also did this for every different legislator. So for every member of the House, for every member of the Senate, in every state, we could tell them, here's how much people in your district make, here's what colleges cost for the people in your district. And we did this for all, it's not just for Tennessee, we did this for all 50 states. Okay, so that was the kind of non-academic side of how we used what we learned about the variation in spatial opportunity. The other thing we did on kind of a more academic sense was to take this and say, well, what difference does that make for people's earnings and their civic outcomes? What we found, let's see here, if we look at earnings, so for the people who are induced to go to college by virtue of living closer to more colleges. So we treated it like a natural experiment. Most people don't know the characteristics of college opportunity close to them. Ask yourself right now, what's the second closest community college to us? Like nobody knows, right? People know schools, people don't really know colleges that much. It's volunteer state community college. But if you look at the impact on people who are induced to go, particularly people by the public 2 years, the increase in earnings for every additional year of higher education is about at 8%. So an additional 8% in earnings for every additional year of education. That's actually kind of industry standard. That's a really well-known finding, but this reinforces findings from the past with more refined measures of geographic opportunity. Find similar measures for voting, that an increase in 1 year of education gets you about a 7% increase in the probability of voting. Okay, so that's all for that. Andreas has given me permission to give a quick plug too at the end here. I teach an undergraduate data science course in the HOD department. This is intended for people who don't have much exposure to programming. It's organized around 3 principles: getting data, analyzing data, and presenting data. The students do get their own data and create projects on it. They've done things like predicting performance in PGA tournaments, the number of undocumented arrivals, and getting how much is it going to cost me to get home, predicting airline prices back to Shanghai in December, and then thinking about the performance of different stock options. There's always a couple students who want to get rich. If you have undergrad students in particular who are interested in this topic and are looking for a place to start, please send them to me. Thank you.
Time for questions.
Please.
Did you consider drive time over straight line distances?
So yeah, we didn't do it in this study, but we're working on that right now. We got data from the Georgia State University system, and we're working in Atlanta right now, because anybody who's from Atlanta or kind of even driven anywhere near Atlanta knows that different times of day, different commutes. So the impact of your drive time on the kinds of classes and the number of classes you take, we think is really important. And so yeah, we're looking at it right now. Thank you.
All right, well, let's thank the speaker again.
Oh, I appreciate it. Thank you.
And to round out the session, let's hear about data science in healthcare from Jesse Spencer-Smith.
Thank you. Thank you all.
Thank you very much for inviting me to come and speak. I'd like to give you a little bit of a different perspective, if I can, perspective from from industry. And we tend to think about data science just a little bit differently. So in the first half of this talk, I'd like to share with you some of the work that we've been doing in healthcare and sort of how we think about data science and the value of data science. And in the second half, would like to talk about trends that we're seeing in data science, which really will have a profound effect in the future, and I think speaks to a lot of the issues that have been brought up here over the last couple of hours. So I'm with HCA Healthcare. We are a healthcare company. We have hospitals, we have ambulatory surgery centers, physician practices across the US, also a few in England. What we really have is a lot of data. We see almost 2 million inpatients a year. We see about 8 million ER patients a year. And long after Vanderbilt started to collect data, we started to collect data in 2013, all of our clinical data. Really impressive that Vanderbilt started so early with electronic health records. The Affordable Care Act and the HITECH Act helped us pull together the data that we needed and to build a clinical data warehouse. And we've had that since late 2013. So we have good, rich clinical data from 2013 going forward, which represents a wide variety of patients across the U.S. With a variety of issues. So it's a great opportunity and really an imperative that we use this data to improve healthcare. So I mentioned that in industry and in healthcare, but even more broadly, in industry, we tend to think about data science a little bit differently. So we see it as an extension of analytics. So you can think of this as thinking about the dimensions of analytical sophistication and the possibility of workflow adoption. There are many other dimensions, but these are two of the most important. So to give you a sense of what's going on here, in workflow adoption, it can start in the historical. So you might do looking backwards. Here you might be looking in the very recent past. So for example, you might have basic analytics going all the way up to really sophisticated data science. So analyses here tend to be backward looking. So a deep analysis you might do on a particular outcome. So in healthcare we talk about root cause analyses. And this will help you think about how you want to do things in the future, but it doesn't affect things right away. You might be looking at an annual report, for example. You might build a retrospective dashboard, which gives you the information a little bit more frequently, with a little bit less of a delay, but still you're not affecting things right away. And then you go all the way up to real-time monitoring, so you have a sense of what's happening right now. And so you can at least respond to things right now. Going up here from basic analyses to a little bit more, here we're just talking about the numbers. Here you're taking one step back from the numbers, and you might take a look at what's often called in business key driver analysis. But really what's going on here is just multiple regression is really what key driver analysis is. You might go a little bit more sophisticated, do some statistical modeling. You might do some natural language processing if you have unstructured data to get a better sense of what's happening. But really, healthcare and other industries are deeply affected when you begin to have more sophisticated analysis with less latency, and that's when we begin to see things such as forecasting, classification, or regression being used, anomaly detection, real-time prediction, prescriptive analytics, not just what happened, not just what were the drivers of what happened, but what would be the next best step. And all the way up to artificial intelligence. This is deep learning models in particular. So I wanted to give you a sense of just two different projects very quickly, and then to move on to trends that we're seeing. So here we had a problem with our emergency departments, an opportunity to see if we could predict volume, because the number of physicians, the number of nurses that you have on staff, and your preparedness really depends on how many people you think might be coming through the door. Well, one way to do this is to do volume prediction just on historical data, so you can get a sense of, at this time of day, for this day of week, for this part of the month, for this time of year, this is how many people we ought to see. So you can certainly do that historical. You can actually put this into a dashboard, but even better is if you have a real-time prediction and you can be looking 4 to 12 hours in advance, and you keep in mind your historical, but you also keep in mind, who do you have in the ER now? How likely is it that they will be seen and they will be actually out of the ER? And that gives you a finer grain prediction while also keeping in mind all the historical that you've learned from before. So ER prediction was one example of something we have going on right now. Another example of work is with Sarah Cannon, which is an HCA organization. So the question here was, we have a large number of pathology reports which indicate whether or not the patient had cancer and what type of cancer the patient had. So you could do this historically, and actually we undertook a project with digital reasoning. HCA took on a project with digital reasoning, Sarah Cannon. As a matter of fact, Christy French, who is I should say, Bill French is the husband of Christy French, who was one of the lead data scientists on this with digital reasoning. So, are you still here? There you are, that's right. So, so your Acre guy over here, contributing to the good of data science, through the whole family. Now, the real power of this is, with natural language processing, we can take pathology reports immediately after they're filed, identify patients and reach out to the patients immediately. Normally what happens is the patient hears some very bad news and doesn't know what to do next. And there's this long period before we can get back to the patient and to say, okay, look, we have resources. Here are some decisions you need to make. There's this long period of time, and that's agonizing. So now it can be an immediate response because we're not trying to sift through and manually read all these reports. Now it's happening, this natural language processing, in real time. And so you can identify the navigators who need to respond and work with these patients. So, I'd like to talk about two major trends that are coming up in data science now. And a lot of them are being enabled by faster processing, GPUs in particular, and GPU clusters. So one of them is auto-ML or driverless AI. These are the ability to generate new models very, very quickly. So this means you don't have data science teams futzing around. You can know what the best possible model is right away. The problem is these are dense and complex. Two is deep learning. With deep learning, you have human-level performance on very complex data sets, images or other data sets that can get very, very good through training. But the problem with these as well is that they're very, very dense. They're very black box. So the two things that these share, though, is that they're all dependent on the data. So you have less manipulation and feature engineering. Now you have the models learning directly from the data. So very little human intervention there. So that means everything that we've talked about right now is incredibly important because now the data is the source code. I believe this is attributable to Jensen Huang, but I'm not positive. So what this means is it's not enough to just store what model you've created. The model is entirely dependent on the data on which it was built. So think about the issues that we've been talking about today. Data science models, predictive models, deep learning models, AI doesn't get rid of bias. It makes it concrete and puts it into the model and makes it difficult to see. So if you're not careful before you actually create your model and attend to where this data is coming from and the properties, the statistical properties of the data, then that will be hidden away in the model. This also means that it's not enough to version your work on software. Now you have to version the data. Because if you want to truly understand what's happening with your AI, with your machine learning algorithm, you must go back to the original source data to understand exactly what was possible to have been to learn. And finally, thank you. I'm going to take about 15 more seconds. No, that's perfect, exactly what I needed to know. The other thing is that machine learning algorithms are really good now. So even if you take away that one indicator, for example, if we're talking about racial bias, you take out race. If there is signal that is race-based because you've had profiling in cities and so most of the arrests have been in this area, or in any area that you'd like to talk about, right? It's going to learn that bias in the data from proxy information. It's great at learning. That's why it's true. The data is the source code. You have to be aware of that. So it's going to require intentional and deep thought to address these issues. That's why I'm so heartened to see such a broad coalition of different scholars in this room and so grateful to be invited to speak to you. So thank you very much for your time.
I was in a meeting recently, and someone was proposing a new machine learning model on the patient chart. And a nurse spoke up and said, I've got like 10 critical warnings on every patient because I work in ICU.
Absolutely.
So you have this information overload. Is HCA, in a practical context, doing anything on that? Or?
Oh, yeah. You know, we've learned that it's very important to work very closely with clinicians and that just another alert won't really do the job. So the question is, what is the workflow and what can you do to enhance that, to augment that? So that's a question that I had earlier. How do you augment what the lawyer does? So the idea is not that we have the signal. The idea is, okay, what do you need to know and when do you need to know it in order to make a better decision? And that's really what the crux, it's the formation of the problem the very first. Other questions?
So to try to connect what you were just saying with what Chris Fonnesbeck said, to connect with what you were saying with what
Yes.
Chris Fonnesbeck said earlier about integrating a data generating model, which comes then from subject matter expertise. What are your thoughts about how to connect this auto ML stuff to then bringing in the subject matter expertise and the data generating models?
It's a great point. The risk and the opportunity is it's possible to build models without any of that. They may not be any good, but it's very easy to build models now. So to bring in a substantive model, what I think of as a substantive model, does help quite a bit. The problem is that it's effortful. So you have this stuff which is really easy to do. You can download software right now, h2o.ai, for example. You can go there, download it, you can build models very, very easily. Putting in substantive knowledge into that, and so you're not just fitting free parameters, you're fitting parameters that fit an understanding is more difficult to do. That being said, you can get much better models if you do that. And I think that's what many people are realizing now, that you can do all the statistical tricks that you want to, but if you really want to have that model improve, then find a way to include expert knowledge within it. Not expert systems, but a substantive model. Mm-hmm.
And I saw one more hand.
Yes. A related issue is the interpretation of the model. I think that goes into how can you incorporate the experts' knowledge about that,
Right.
And how important that is to HCA.
Yeah, that's a very, very good question. So I mentioned before that these models, that as we've discussed before, can be very black box. And interpreting what's happening with the models can be difficult. And often, after you fit a model using traditional methods, it's kind of too late. Because you see really interesting adversarial examples where the misclassification can be, you can get at the misclassification by just adding noise. The way that an AI will learn is entirely different than the way that a human would learn. So one way to begin to address that is when you're first creating the model is to do so in such a way that you can understand a little bit better, put some constraints on how it's learning. That's the substantive models. And there are other alternative approaches which allow you to see exactly what is being learned. But I think you put your finger on it. Understanding exactly how it's learned and how it's operating is very, very important. There are a lot of post hoc ways to suggest why a decision has been made. So I would say there are multiple approaches. It's an area great for research. It's certainly something that we are aware of and that we realize that we need to balance. Simple model, which may not capture everything, but can be utterly explainable, versus one that performs somewhat better, but may be black box. And those must be weighed. And sometimes the black box is the better way to go. Sometimes explainable is more important. But basic research also I think is going to be very, very important here. So the computer scientists, mathematicians, absolutely in the room. Thank you.
Thank you very much. And
Thank
let's
you.
thank the speaker and all of our speakers in this panel. All right, we're going to have a short...